Hi everyone. I will talk about our recent work on parameterized approximability under ETH. This is a joint work with Venkat, Xuandi, Yichan, and Kerwin. Parameterized algorithms and approximation algorithms are two powerful approaches to dealing with hard problems. Approximation algorithms relax the goal, looking for solutions close to the optimal one. Parameterized algorithms relax the running time, allowing algorithms with running time upper bounded by f of k times polynomial of n. Such algorithms are called FPT algorithms. Parameterized approximation algorithm is the combination of these two methods. Recently, there have been many breakthrough results in the study of parameterized approximation algorithms. To solve hardness of approximation, one usually uses the famous PCP theorem. A central problem in the study of parameterized approximation algorithm is to prove a parameterized version of the PCP theorem. So let me start with an introduction to the PCP theorem. To verify whether a proof is correct, a naive verifier needs to check every bit of the proof. A PCP verifier only needs to read constant number of random bits and has constant error probability. More precisely, if the statement you want to prove is correct and has a proof for the naive verifier, then there exists a proof that the PCP verifier accepts with probability 1. If the statement you want to prove is not correct, then no matter how you write your proof, the PCP verifier can only accept with 1 minus epsilon probability. Informally, the PCP theorem says that there is a polynomial time algorithm that can convert a naive verifier into a PCP verifier. Formally, the PCP theorem says that there is a PCP verifier for the 3-set problem with n times polylog n proof length. The PCP theorem has connections with many areas such as cryptocurrency, meta-complexity, property testing, coding theory, and quantum computation. The biggest application of PCP theorem is to solve hardness of approximation. The bridge connecting the PCP theorem and hardness approximation is constraint satisfaction problem. In a CSP problem, we have a set of variables and some constraints. Each constraint has a constant number of inputs. The goal is to find an assignment to the variable such that all constraints are satisfied. We can transform a PCP verifier into a CSP problem. Suppose that the PCP verifier has proof length n. We introduce a CSP problem with n variables. Each variable is expected to guess the corresponding bit of the correct proof for the PCP verifier. For each randomness, the PCP verifier queries some location of the proof. We introduce a constraint for the corresponding variables. It is easy to see that the fraction of satisfying constraint of the CSP problem is equal to the probability that the PCP verifier accepts the proof. The PCP theorem can be reformulated as it is NP-hard to decide whether a CSP instance is satisfiable or any assignment can satisfy at most 1 minus epsilon fraction of its constraints. We call such CSP gap CSP. Since we are interested in parameterized approximation, a natural question is what does a parameterized PCP theorem look like? To get a parameterized version of PCP theorem, we pick the number of variables as the parameter for the CSP problem and rephrase the statement of PCP theorem as there is no FPT algorithm to solve the parameterized gap version of CSP problem. This is the parameterized version of PCP theorem. It is called PIH. In 2024, we proved PIH under the exponential time hypothesis. In the proof view, we gave a PCP verifier for a 3-set that reads constant number of lines from the proof, where each line contains at most n over k bits and the proof contains at most exponential of poly k lines. One might ask, why not just apply the classical PCP theorem and divide the proof into k lines? In fact, the state-of-the-art PCP theorem has a polylog n factor blow-up of the proof length. It is still a big open problem whether there exists a PCP for 3-set with linear proof length. In our setting, we can remove this polylog n factor. In this talk, we give a short parameterized PCP for 3-set problem, which reduces the number of lines in the proof to almost linear of k, with the price of increasing the bit in each line to n times log k over k. As applications of our result, we obtain improved lower bound for approximating parameterized CSP K-clique, maximal coverage, and exact K-cover. These results have been improved by Wagner, Kassik, and Minzer based on our proof framework and high-dimension expander graphs. Our proof framework contains 2 steps. First, we reduce 3 sets to CSP with linear and parallel constraints. Then we design PCP verifier for this CSP problem. We define a class of CSP problem called vector value CSP. The alphabet of such CSP is a vector space. The constraints are either linear constraints or parallel constraints. By parallel constraints, we mean a sub-constraint applied to every entry of 2 vectors. Note that if all constraints are linear, then this CSP becomes a linear equation system, which can be solved in polynomial time. If all constraints are parallel, then we can solve this problem by enumerating all the assignments to each entry, which can be done in FPT. We saw that vector value CSP with both types of constraints are hard under ETH. We reduce 3 sets to vector value CSP. Previous paper gets a k-square variable vector value CSP with n over k dimension. In this work, we use Mark's result on sparse CSP to get linear k variable CSP with n times log k over k dimension. The second part is to design PCP for the vector value CSP problem. Suppose Alice wants to convince you that a vector value CSP instance gamma is satisfiable. She could give you a proof that the parallel part is satisfiable and a proof that the linear part is satisfiable. But she also needs to ensure that these 2 parts share the same solution. So we need PCP of proximity. The statement to prove is not just gamma is satisfiable, but X is the encoding of a solution to gamma. So we need to encode the assignment to variables. The vector value CSP allows us to do parallel encoding. We write down the assignment to variables as column vectors. Each column vector corresponds to a line in the proof. Then we pick an encoding function and apply it to every row vector of the assignment. As you can see, parallel encoding does not increase the number of bits in each line. It also keeps the number of lines depending only on the parameter k. This is how we get rid of the polylog n factor in the classical PCP proof. In our previous paper, we used Hadamard code, which causes exponential blow-up of the parameter. In this work, we use Reed-Muller code, which gives us almost linear blow-up. Now let's give a PCPP for parallel constraints. In this case, we have the same circuit applied to every entry of k vectors. We can create a new circuit which, given a Reed-Muller code, decide if it is a Reed-Muller code of a solution to the original circuit. Then we use the result of Benson et al. That circuit set has almost linear PCPP, and it can be applied parallel. Then we are done. The hard part is the linear constraints. Suppose we want to design a PCPP for the linear constraints over variables x and y. First, we consider their Reed-Muller codes. The Reed-Muller codes treats the input message as the degree n variable polynomial. The code word is the truth table of this polynomial. By the result of coding theory, these codes have a systematic part, which is equal to the input message. We define a new vector z as the Reed-Muller code of y minus the Reed-Muller code of matrix times the Reed-Muller code of x. Observe that z is degree 2 the Reed-Muller code. If the linear constraints are satisfied, then the first k entries of z are 0. Our PCPP verifier for the linear constraints expects that the proof contains x hat and y hat, which are supposed to be the read-Muller codes of x and y. The proof also contains z hat, which is expected to be the vector z. We claim that the linear constraints are satisfied if, first, the input vector x hat, y hat, and z hat are close to some read-Muller code, and second, the first k entries of the read-Muller code close to z hat are zeros. And finally, the read-Muller code close to z hat is, in fact, the vector z. The first two items can be handled like parallel constraints. We need to provide an additional proof pi for these parallel constraints. To check that the input vector z hat is close to the vector z, we randomly pick an entries and check if they agree on this location. This is because if z hat passed the first check, then it is close to a truth table of degree 2D polynomial. If two degree 2D polynomials are not equal, then they disagree on a random point with high probability. To summarize, in this talk, we give a PCP for 3 set that reads constant number of lines from the proof, and the proof has near linear k lines, and each line has n times log k over k bits. An open question in this direction is to prove PIH under W1 not equal to FPT, which requires a reduction from a general CSP to its gap version. Note that our reduction solves a special case of this question where the constraint of the input CSP consists of linear and parallel constraints. Thank you.